Okay, so these projects is a disclaimer. So these projects are kind of like my own recipe that have their own like a little twist. And in order to get the most benefit, you really don't have to know anything about electronics for right now. In order for you to get the most benefit is I want people to basically watch the videos and get involved in it physically. Get the microcontroller and physically get involved and wire it up and copy and paste the code and all that and see how it works. And just on that type of level is great. Like, I mean, I got all this. Some of you guys are giving me Google comment or Gmail comments, and you guys are looking at it a little bit too deeply, I think. And you're like, well, I want to make a pizza and all that stuff, but how do you make the pepperoni? What's the process of making pepperoni? It's like, whoa, I don't know how to make pepperoni. I just know how to make the pizza. So remember that don't look too deeply at first, but as we progress, it is going to be kind of harder and harder to understand. Do the best you can, put on the headphones, and just ask questions. Ask questions. What is this about? What is that about? Always ask questions. So I put this over here prerequisite for easy learning. This doesn't mean that people can't watch this. I'm just saying I'm catering to people who've taken these courses before, who've taken the engineering classes and all that stuff, who has, and maybe are worked at a place for many, many years and finally, they don't work there anymore. They're getting back into it again. And the reason why is because these guys earned it. These guys who took these courses earned it. These guys were right here, they earned it. They went through the hell of getting this degree. And also, it's also catered to people that want to take ideas. Hey, to take ideas, it might help you guys out. There's stuff like that. So now, if you have any questions, if you're bashful to leave something down, go ahead and email me at andrewchen80@gmail.com. I know people are bashful. They don't want to leave comments because they don't want to look stupid. They're like, oh man, you don't know what an ID is. Oh, you don't know what a variable is. You don't know what blah, 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 blah. Okay. Yes, there are people like that on the internet. I don't know why. Can't we all just get along? Okay. So put your headphones on. Headphones. Put that thumbs up. And now, enjoy the show. Hello, everyone. Welcome to the Bard Show. I am your host, Andrew Dunlop. How is everyone doing out there today? I hope you guys are doing well. And I'm just, let's go ahead and talk about our topic today. So engineering manager says we're going to create a dimmer switch that will light up an LED. We're going to use a development board, potentiometer. It's one of those trim pot things. And we're going to implement the analog out or the output of your code, okay? The hint, do not think too deeply, okay? And let's go ahead and stop the video and let's design the project. All right, so our topic today is called analog to digital converter, okay? We're going to discuss pretty much all the questions, who, what, when, where, why, to the analog to digital converter. Now, I'm only going to cover a very superficial amount because this topic is deep with mind-bending mathematics. So this is a topic that's a very important topic, and it can be kind of, this topic is actually, we've done the DAC before, but this is the analog to digital converter, which means this is where we talk about sensors. This is a very important topic, and it's a very involved topic, okay? So in ADC, what is an analog digital converter? It's an analog digital converter. It takes the varying voltage from 0 volts to maximum N volts, and it converts the volts to a binary code, so the processor can understand. So it doesn't understand volts; it only understands ones and zeros. So then the programmer needs to harness this data so human beings, I don't think there's any Nagas out there, but who knows, can understand it. And in our case, we're using it to read from 0 to 3.3 volts. There are other analog converters that go from 0 to 5 volts, 0 to 10 volts. That's why it's maximum of N volts. All right, so why is the analog converter so important? Well, for embedded systems, it all depends on input. So maybe we need a light sensor, we need temperature, a microphone, vibration. It could vibration from a person's heart. It needs any type of sensors. It could be ultrasonic sensors. It could be humidity sensors. All sensors has to be somehow converted into a voltage, and then from that voltage, it then has to go to into a digital code. Now, how does it work? This is how it generally works. First, there's the analog input. There's scaling. So there's a circuit in there that scales, and then it kind of determines where the 3 volts are. There's many things going on because it's not a consistent value. Okay, there's a filter. So sometimes when the voltage goes into the microcontroller and all that stuff, when it's sensing, there's a filter. So there's a lot of noise in there. So there's a high pass filter in case there's some sort of squeaky squelch, and there's a low pass where it's like it doesn't want all the low garbage. So it wants to basically contain all the good stuff in a band pass type filter. The sample and hold circuit is sort of a circuit that uses more of a digital filtering system, and it samples it, and it takes the best value, and then it goes into a switch. This is a switch right here. The mute is a switch, and then the switch is wherever it goes. Then it goes to the analog to digital converter. The analog to digital converter has many. It has op amps, and so it determines the value. It converts the voltage to from the op amp. So if the voltage is if the plus minus is greater than that, greater than the other voltage, then it'll do a 0. If it's greater than, or it'll do a 1, and so on and so on, so until it creates some kind of off on code. Okay, so it's kind of complicated. It's hard for me to discuss, but just kind of like there's a bunch of stuff that goes in the background. How it works. So we kind of saw it. Basically, what it does, it takes a sample. So as the voltage comes in, it takes a sample, and it takes a sample, and it then shoots the sample to the circuit. The circuit then determines of where it's at. Like I said before, the more resolution the sample has, the more distinct, the more faithfully it can reproduce that phenomenon. So if I'm talking to a microphone, it can sample it. If it can sample it as high as it can, it'll actually sound like a real voice rather than sound like a robot voice. You know what I mean? So that's how it kind of works. A Nyquist, then it goes into a Nyquist system. So it doesn't sample it. What it does, it speeds up. So this is a sine wave. So anything from we hear from 20 hertz to 20,000 hertz. But then on your CD player, back in the old days, when we had CD players, but it was sampled at 44.1 kilohertz, and everything is sampled at twice the frequency to prevent aliasing. Okay, so aliasing is a little bit beyond this topic right here, but it's basically aliasing is pretty much it will mimic a signal, and so it looks like a signal, but it's not a signal. So it's kind of like it has its own name. That's aliasing. The generic formulas to be used to predict ADC is D equals VI VR times 2 to the n. So it's pretty much the same thing as the digital to analog converter, but kind of in reverse. But it's still the same formula, just arranged completely different. So D is the output value. That's what it produces, all the ones and zeros. I think it's in a hexadecimal code, but you can check me on that. There's the input voltage. That's pretty much going from 0 to 3.3 volts. That's going to vary back and forth. So like in a temperature sensor, if it's cold, it's going to has a low voltage, and then it's basically going to reach sort of a lower value. As the temperature sensor, say, it warms up, it's going to give you a higher voltage, and then there's a scaling that is involved. 2 to the n is the resolution. So that is how many points can go to that wave. Okay, and the reference is pretty much the stamp, is what is your voltage going in. So in our case, it's 3.3 volts. It depends on what circuitry, but in our case, it's 3.3 volts. But this is pretty much the general formula of how it works, and this is what they're aiming for at all times. Okay, so what is the resolution of the nuclear FR11RE embedded device? What is the reference voltage? I already told you that. If I measure 1.58 coming, what would the D value be? That's kind of good to know. So the value that we have, you just go to your data sheet. It's the data sheet you need to look at is not the nucleo, whatever it is. It is the chip. So the chip is STM32F4111, the chip itself. The development board is just, it's like the arms and legs, you know. We want to know what's in that brain, okay? So the CPU, the operating voltage is, where is it? There's 12-bit DAC channels. There's about 10 or so. And then where is it on the device? So you see how the peach-colored analog in, and then there's like a line in there that says A1 and PA1. It can be A1 or PA1, okay? You can't use both, A2 or PA2. They're both sort of connected the same, PA, A3. I like to use these, A3, A4, A6. That kind of helps me out. I don't. You can use these too. You can use PA5. PA5. You can declare that. So analog out or analog in. Excuse me. Analog in. And
all right. So the topics we have today is the digital to analog converters. These are called DACs. This is a huge topic. I'm only going to cover just a very superficial amount. You could take, there's courses, and you can get a whole degree in this, you know, a whole, but just in this topic alone, it's huge. So what is digital analog converter? We're going to talk about some basic formulas. We're going to talk about what device uses digital analog converters, how to evoke a digital analog object to your code. Okay. So the materials needed. This is a very simple section. All you need is a device, a Nucleo L476RG. This is just a device that has an analog out feature. There's a lot of devices that don't, so you might want to make sure before you go to Amazon or Digitech or whatever it is, DigiKey or something like that, that it has an analog out. How do you know? You're just going to have to look at the data sheet. Okay, you must have an oscilloscope. So, I mean, if you don't have an oscilloscope, you can use an analog. I think it's called Analog Discovery. They have a oscilloscope. You're still paying, a good fortune for it. This is a digital scope, so this kind of has an output of it. And you must have a computer code. I assume you guys all have computers because you wouldn't be able to watching this on YouTube. But so I guess you could watch it on your phone. This right here, when you look at it, you see you see analog in, and then you see one small word that says analog out, and it's hooked up to PA4. So that's how you know it goes to PA4. And that's the analog out. Okay, what is a digital analog converter? So basically, it's a digital analog, takes the binary and hexadecimal word from the microcontroller, converts it from a variable voltage from 0 to 3.3 volts at a frequency. So this is the ones coming in, the ones that are already in there. There's your digital analog converter is inside this chip. It then gets you don't really see it, or you could put it onto a scope. This is supposed to be like a speech waveform, and it goes out your speaker so you can actually hear it. So you're going to discover that there's other ways of getting a similar output like that. It's the pulse width modulation. That's coming up pretty soon, but right now we're just going to deal with just the analog out feature. Okay, so what are the design parameters? Okay, we're going to talk about this. Here we get into some little bit of algebra, little bit of maybe calculus. Maybe that's considered calculus. I'm not quite sure. All right, this is the voltage out. This is what you get. D is the binary word. The D can vary from 0x000 all the way to 0FFF. Okay. And the voltage R is your reference. Okay. And 2 to the N is the resolution. Okay. So the resolution is the higher the resolution, the more faithful it can produce that sound. So if you have a very high resolution rate, such in your monitor, you notice the pixels get smaller and it gets more tighter. The picture comes in better. If the resolution is not as fine, then the picture gets more blocky. So that's the best way. So the same thing with sound. The higher the resolution, the faithfully it can produce the sound, like of a dog barking or a music out of a guitar or something like that. So that is the same. That is what that means. The word is basically instead of just a byte, a word is just a set of instructions. So it could be 8-bit, 12-bit, 16-bit, 13-bit. I think sometimes our computers are like 64-bit words coming in, but this is a 12-bit. Well, no spoiler alert, but anyways. So this is your typical output of an 8-bit system. See how it's kind of like in these steps. The 1/8 the step. It's 0, 0, 0, 2 eighths, 0, 0, 1, 3 eighths of the is 1, so on, so until you get to 1, 1, 1, and that's basically 8 bits. It's quite rough, but this is a very easy way of understanding that like a half of it is 4. What's 4? Let me think. Is 8. Okay. Or 0 to 4, excuse me. 4, that makes sense. It's 4. Okay. So hello. So this is the parts list. This is going to help you guys to get going. So hope you guys got a development board. Then there's the it's a trim pot, okay? It's like a volume knob, okay? I have a hard time pronouncing that word. A diode, it doesn't have to be red. It can be blue. or yellow. A resistor, make sure it's 330 ohms resistor-ish. Doesn't have to be exact. 3, maybe 400. That's okay. The higher the better. It's going to be a little more dim, but don't get it too low. Computer, I hope you got a computer, USB, and a breadboard. That's a breadboard. Remember on the breadboard that the minuses run parallel, and the pluses, they run in parallel to each other. So they're running like columns, okay? And the these are like rows. So these are rows, and these are these individuals. So get that, and I'll see you at the CAD section. All right. So this is the AutoCAD section. I already got everything built, so you don't have to look at it. So people who are new, the red circles are connecting nodes. And if it crosses over, that means it's not connected. Okay, so let's go ahead and take a deeper look at this. I have a 10K trim pot right here. You see where the X is going back and forth. There's the LED. It's over here. It has a 330 ohm resistor right here. Now let's dive in deeper. I have it powered. We don't need a lot of current because it's going right back into its old system. So this is fine. Take this thing right here. It's fed into one of the legs of the 10K trim pot, and then we have the knob part where it varies the resistance value. It's basically connected to PA0. I have it connected to PA0. You can connect to PA1, not PA4 though. Can't do two at the same time. So anything that I showed you on the list there, on the diagram, excuse me. So PA0 is connected there. Now I have PA4, which is, we know that's analog out. That's connected to the diode. Okay, so let's go ahead and just go out a little bit farther. There you go, guys. Take a picture of that, and I'll see you on the Code Talk. Okay, so here we are in Code Talk, and here we are at Code Talk, and we're just going through it. Comment. We open it up. I assume you guys should know that by now. Now we go ahead and we declare our variables: analog out, analog in. I call it DAC, PA4, and that's PA0. And we got hashtag define time as 1 millisecond. You can use that, you cannot. Sometimes I do it. And now we're at the main, and now there's the while loop, and look at that. That's it. It's beautiful. ADC, whatever value of ADC is now DAC. And I know you thought it was, yep. So let's go ahead and go to the proof section. So we got lucky on that deal. So that's the LED. It acts like a dimmer switch. So there it goes. It's all the way full brightness. And then it goes, we can turn it all the way down. Okay, so this is part one. That was pretty easy. But as you know, it's going to get a little bit more challenging. Okay, I'll see you next on the Engineering Bar Show. I love everyone who's watching it. So everyone, just thank you.